Hello, everyone. We'll start with mechanics, and particularly the surface tension is something that we want to cover today. If you see your course, the syllabus for mechanics, it covers the mechanics of single particle, mechanics of a system of particles, surface tension, ideal fluids and viscosity, oscillations. Among all this, I'll be basically covering surface tension, and mechanics of ideal fluid and viscosity, and my colleagues will be covering the rest of the parts. In surface tension, which is the topic today, we will understand the surface energy and the definition of surface tension, angle of contact, excess pressure on curved surfaces, capillary rise, equilibrium with vapor pressure over curved surfaces, which is part of your syllabus, and we'll go into more advanced topics. So surface tension is an effective within the surface layer of a liquid that causes the layer to behave as elastic sheet. Thus, the surface of any liquid behaves as if it was covered by a stretched membrane. Surface tension is measured in units of force per unit length. So basically, a square element on the surface of a liquid is subject to tension, which is 4 per unit length in all four sides. This tension is the result of intermolecular forces. It makes the surface behave as if it was a stretched membrane. In general, surface tension is the elastic tendency of fluid surface which makes it acquire the least surface area possible. The surface tension allows water striders and many other insects, usually denser than water, to float and stride on water surface. At liquid air surfaces, surface tension results from a greater attraction of liquid molecules to each other due to cohesion than to the molecules in the air due to adhesion. The net effect is an inward force at its surface that causes the liquid to behave as if its surface were covered with a stretched elastic membrane. Thus, the surface becomes under tension from the imbalanced forces, which is probably where the term surface tension comes from. Because of the relatively high attraction of the water molecule for each other through a web of hydrogen bonds, water has higher surface tension compared to the most of the other liquids. Surface tension is an important factor in phenomena of capillary. Surface tension has the dimension of force per unit length or energy per unit area. The two are equivalent, but when conferring to energy per unit of area, it is common to use the term surface energy, which is more general term in sense that it applies also to solids. In material science, surface tension is used to either surface stress or free energy. Now, the SI unit of surface tension is Newton per meter or joule per meter square. Its dimension is this. We have some of the fascinating illustration of surface tension. We see this phenomena in day-to-day life. Small insects like water strider can walk on the water because the weight is not enough to penetrate the surface. Now, floating of needles. When you place a small needle, you can also see that it's floating on the surface of the water, even though it is several times as dense as water. If the surface is agitated to break up the surface tension, then the needle will quickly sink. Another fascinating illustration is surface tension and droplets, responsible for the shape of liquid droplets on top of, say, some leaf. Although easily deformed, droplets of water tend to be pulled into a spherical shape by cohesive forces of the surface layer. Surface tension is caused by the effect of intermolecular surfaces at the interface. Surface tension depends on the nature of liquid, the surrounding environment, and temperature. Liquids where molecules have large attractive intermolecular forces have a large surface tension. As Shumir wants to say is the liquid whose molecules have larger attractive intermolecular forces will have a larger surface tension. This figure shows that intermolecular forces acting on a liquid particle, adhesion and cohesion, are the two kinds of intermolecular forces that we are dealing with. Within the body of liquid, the fluid, cohesive forces act on the particle in all directions. When the particle on the surface of the liquid, both cohesive bottom and the adhesive, the top surfaces, act on the particle. So in simple, on the surface, what happens is the forces in the interface towards the air is actually less strong, and that is why you have a surface tension across the surface. If we try to explain it in terms of energy, a molecule in contact with the neighbor is in a lower state of an energy than if it were alone, not in contact with the neighbor. The interior molecules have as many neighbors as they can possibly have, but the boundary molecules are missing neighbors compared to the interior molecules and therefore have higher energy. For a liquid to minimize its energy state, the number of higher energy boundary molecules must be minimized. The minimized quantity of the boundary molecules results in a minimization of area. So we understand that it's a natural tendency to actually minimize the energy and go towards the ground state, what we say. And that is why, considering that the molecules on the outer edges or on the surfaces have higher energy, the surface area tends to always minimize. So surface tension actually comes because of the fact that the liquid actually wants to reduce down its overall surface area. The surface tension represented by the symbol psi is defined as the force along a line of unit length, where the force is tangent to the surface but perpendicular to the line. The thread will be pulled towards the interior of the film by the force equal to 2 psi L. So it's basically the two factor comes because of the soap film has two sides, hence two surfaces. The surface tension is therefore measured in forces per unit length. An equivalent definition is work done per unit area. As such, in order to increase the surface area, a quantity of work say A is needed. This work is stored as potential energy. Since mechanical systems try to find a state of minimum potential energy, a free droplet or liquid naturally assumes a spherical shape, which has the minimum surface area for a given volume. The Laplace's law for pressure, considering a surface curvature, looks like this, where P is the pressure, rho is the surface tension. So if we have to understand the pressure and the relation with the surface pressure, and we have to understand its consideration in terms of the curvature and the surface tension, then this would be something that we have to deal with. The factors that affect surface tension are impurity, because that changes the surface tension a lot. A highly soluble substance like salt increases the surface tension, whereas the strongly soluble substances, less soluble substances like soap decreases the surface tension. Oxygen in the atmosphere is known to decrease the surface tension of various substances. The part which is important is the effect of temperature. In general, surface tension decreases when the temperature increases because cohesive forces decrease with an increase of molecular thermal activity. The influence of the surrounding environment is due to the adhesive action liquid molecules have at the interface. So when we try to understand the surface tension and the effect, as we increase the temperature, you can see that with the increase of temperature, the surface tension of water actually reduces down. This is because the cohesive forces decrease as molecules vibrate at a higher frequency when temperature is increased. Another concept that we have to be aware of is the contact angle. The contact angle is the angle that is formed when liquid comes in contact with a solid. The magnitude of the contact angle depends preliminarily on the ratio of the adhesive forces between the liquid and the solid and the cohesive forces of the liquid. When the adhesive forces are large in relation to the cohesive forces, the contact angle is less than 90 degrees. The angles less than 90 degrees will result in a tendency of the liquid to wet the surface. There are two kinds of contact angles, a static contact angle and dynamic contact angles. A drop of liquid placed over a non-absorbent solid may reach equilibrium. When this condition occurs, the contact angle is a static contact angle. High viscosity liquids may require a prolonged period to reach a static angle. In absorbent surfaces, when the liquid penetrates the surface substrate, the contact angle changes continuously with time. For certain materials, the process time is critical to workflow. To measure the dynamic contact angle and the rate of absorption and expansion, it becomes necessary to capture an image sequence over the process. The measurement of the contact angles can be done for a water on glass, water on soap, water on water repellent fabric. To do this, we need to use a digital camera with the macro capabilities to measure the angle and to be photographed. We can do this just by another way is to by observing the differences of contact angle of water on different materials. The concept which will enable us to measure surface tension is capillary rise, which also has many applications. When the water comes in contact with a capillary tube, a meniscus will be formed, resulting in a net upward force. As water climbs into the capillary, the weight of the water column will offset the capillary force until equilibrium is reached. The smaller the diameter of the capillary, the higher the rise. As soon as the liquid comes in contact with the walls of the tube, a contact angle is established. In the case of water and gas, this angle is small, resulting in a concave meniscus. The surface tension acting on the fluid at the point of the contact of air, water, gas will create upward force that will make water rise in the tube until the weight of the water column balances the upward surface tension component. We can do that mathematically while considering a capillary tube of uniform bore dipped vertically in a beaker containing water. Due to surface tension, water rises to a height h in the capillary tube. For a surface tension T of the water that acts inward, the reaction of the tube, which is outward. Now R has to be equal to T in magnitude, but opposite in direction. We're talking about the balance. This reaction R can be resolved into two rectangular components, horizontal component and the vertical component, acting upwards. The horizontal component acting all along the circumference of the tube cancel each other, whereas the vertical component balances the weight of the water column in the tube. The total upward force circumference of the tube becomes this. This upward force is responsible for the capillary rise. As the water column is in equilibrium, this force acting upwards is equal to the weight of the water column acting downwards. This can give us the height at which the water column would actually rise, and can be used for experimental measurement of surface tension. For doing that, what we need is a needle fixed in the capillary tube. The tube is raised and lowered until the tip of the needle just touches the water surface. The traveling microscope is focused in the meniscus of the water in the capillary tube. The reading R1 corresponding to the lower meniscus is noted. The microscope is lowered and focuses on the tip of the needle, and corresponding reading is taken as R2. The difference between R1 and R2 gives the capillary rise H. The radius of the capillary tube is determined using the traveling microscope. If rho is the density of the water, then the surface tension of the water is given by this equation. G is the acceleration due to gravity. Another way of measurement of surface tension is by using Dunois ring. It's a platinum ring placed over the surface of the liquid. The force required to separate the ring from the surface is measured with a high precision table. Water adheres to the ring. The force required to separate the ring from the surface is required to overcome the surface tension of the water adhered to the ring as it is lifted. If we study further on the contact angle for free body, the phenomenon that influences the rise of the drop of the fluid in a capillary tube is relative value of the adhesion forces between the walls of the fluid and the cohesive forces of the fluid. The ratio of these forces determines the angle that the fluid forms when it comes into the contact with the solid. If the angle is small, the liquid wets the solid and a concave meniscus is formed in a capillary tube. This figure shows a water droplet on the solid surface. And the forces like solid air, liquid solid, and air liquid surfaces, interfaces. Note that the point of contact of air, liquid, and solid is in equilibrium. Because of the tension active forces are functions solely of the ratios of the cohesive and adhesive forces, the angle of contact will likely take value that achieves minimum energy, which is the equilibrium. Thus, at any given temperature, the contact angle depends solely on the materials involved. The contact angle between a solid and liquid can be observed by placing a drop of liquid on the flat surface of the solid. Contact angles are small when cohesive forces are small in relation to adhesive forces. Small contact angles result in a tendency of the fluid to wet the surface of this solid. This figure shows a water droplet on the solid surface. When cohesive forces are large in relation to the adhesive forces, contact angles tend to be large. Under this condition, the liquid will tend to form droplets on the surface of the solid. When the opposite occurs, a small cohesion in relation to the adhesion, the angle of the contact will tend to be small and the liquid will tend to wet the surface of the solid. Some textile materials are treated in such a way that adhesion to the water is reduced, making them water propellant. When we deal with solid moisture that is retained in soil, it is basically the interconnected pore space in the solid that holds the water due to surface tension effects. The pores in the soil act like capillaries, the concept we just introduced by, that absorb and retain the water. The smaller the pore, larger the energy with which the water is retained in the solid. Whereas the large pores are easy to drain, the small ones are difficult to drain. So the various retention energy is actually shown here. Like various type of the solid do have different water holding capacity. Now the soil texture influences the shape of these curves. The soil with large pores tend to hold less water and drain quicker than the solids with the finer structures. In simple, soil are porous media that can be viewed as bundles of complex capillary tube of different sizes. If you have a coarser structure or texture of the soil in the larger the pores, thus one can expect that in coarse structure, soil's capillary rise will be smaller than in fine texture soils. If soil moisture is measured from the surface of the water table upwards, it can be seen that the texture has an important effect in the distribution. The concept of capillary tube also is important when we deal with mercury and water. The comparison is important. When water and mercury are each placed in a capillary tube, a different meniscus will be formed. Water will form a convex meniscus, whereas mercury, because of its larger cohesive forces, will form a concave meniscus that will behave in an opposite manner as water. When the adhesive forces between the liquids and solid are larger than the liquid's convex, convective forces, the meniscus in the small diameter tube will tend to be concave. For example, water in a glass. This is because the resulting small contact angle will tend to weight the surface of the glass. You can observe this with a straw and a cup of soda. If adhesive forces are smaller than the cohesive forces, the meniscus will tend to be convex. For example, mercury in glass. The application of surface tension is something that makes it so important to study. It has various applications in soap solution. Considering the surface tension of soap solution is less, it can spread over a large area and wash clothes more effectively since the dirty particles stick to the soap molecules. In case of soldering, addition of fixed flux reduces the surface tension of the melted tin. Antiseptics like Dettol have low surface tension, so they spread faster. Surface tension prevents water from passing through the pores of an umbrella. The duck is actually able to float on water as it feathers secret oil that lowers the surface tension of the water. We can just have a few standard numerical problems just to have an idea exactly what we are studying. A glass slide is in contact with a water surface along with one of its sides as shown in the figure. We have to calculate the magnitude of force required to overcome the surface tension as the slide is lifted from the water surface. Now basically, if you know the surface tension, the force is nothing but the surface tension into the perimeter. Considering the definition of surface tension is force per unit length. So in this case, the contact surface is the perimeter, which is 10 plus 10 plus 0.02 plus 0.02 because it's a square. It's a rectangular shape, and that gives us the force. The second question is, consider the example of a steel pin floating on water. What is the angle of tangent to the water surface at the point of water air solid contact with respect to the horizontal. The surface tension is given. Here, the vertical component of the force resulting from the surface tension at the point of the water air solid contact will balance the weight of the pin. So basically 2F sine theta will be same as the weight. Now F, which is the force, is due to the surface tension along the pin. So it will be basically the surface tension into length L. So this problem also cites about some agricultural spray equipment which can atomize liquid particles to a very small diameters. If the surface tension of water is given, what is the pressure inside the water droplet with 0.05 centimeter of diameter? So if we consider the hemispherical part of the droplet, the surface tension forces act on the perimeter of the hemisphere, and the internal pressure of the droplet can be uniformly over the surface of the hemisphere at equilibrium, because that's how the droplet is formed. The force resulting from the surface tension is equal to the force resulting from the internal pressure. So considering the internal pressure is P, the force will be this, whereas the surface tension area is the periphery into this surface tension. Thus the value will be something like this.